We are happy to have Jan Johannsen as a speaker this afternoon. He's from the Fraunhofer IAPT, our booth neighbor. The Fraunhofer IAPT is actually the only Fraunhofer Institute focusing solemnly on additive manufacturing and also on the entire process chain. Jan, we're happy to have you.
Yeah, thanks Andreas. I will give a presentation about our experience with beam shaping within the SLM process, or laser powder bed fusion process. I will focus on on our experiences with the materials AlSi10Mg and titanium 64. But I will also show some examples of steel alloy, for example. Just a brief agenda. So I will start and introduce what we are doing, our experience with beam shaping, how our path were to the nLIGHT laser system. I will show for some materials the advancements we made with processing with beam shaping, and also very briefly I will touch to some challenges we are noticed which are occurring when using beam shaping. I mentioned we are located in Hamburg. We were founded 5 years ago and included into the Fraunhofer family. We are approximately 100 employees, and as Andreas kindly introduced, we are dealing with the whole process chain of additive manufacturing, from the start, from the idea of a part through the processes, post-processing, and also the digital framework of the processes. Briefly, our mission and vision statement. We have the mission ourselves to introduce the additive manufacturing to the industry, particularly in Germany, but also Europe and worldwide, and with a goal to create resource-efficient and green products for the future. And of course, our vision is, if any of you guys have problems with dealing or question with dealing additive manufacturing, please come to us. So, briefly introduction, what is the motivation part of why we want to use beam shaping? So, if we are looking at the laser powder bed fusion process, the productivity somehow was limited by the laser power we can introduce into the systems, or into the material. At the beginning, quite a challenge was to get high laser power, so how many watts can my laser produce or put into the system. But then, if the number increases or increased, we found out, or the research community found out, it matters how the energy is distributed into the material. Shown at the bottom right of the graph is, if we simplify the Gaussian profile, we have in the middle of the profile a high intensity peak, which might lead to evaporation of material, and so the chemistry, the alloy changes, and it's not what we want to produce. On the same time, at the edges of the Gaussian beam profile, the energy is not high enough. So, quote unquote, we lose some energy because the energy is not high enough to melt the material. So there is the idea, if we can distribute the energy more clever, like a ring shape, for example, or other possibilities, we can couple more energy into the material and increase, therefore, the productivity. So, what is shown here is on the top right. You can see two different beam profiles we used, like in yellow, a typical Gaussian beam profile, and then we created a beam profile, a ring-shaped beam profile with the same size, the same diameter, to compare a Gaussian and a donut profile. On the table with the edged cross-section of a single weld track, you can see for different laser powers and scan speeds a comparison of the melt pool for the Gaussian and for the donut profile. And I want to highlight at this slide, for the Gaussian profile on the left, you can see some defects like protrusion or cracking, while for the donut profile this was not visible for the wide range of combination of process parameters we used. And also what you can see, quite interesting, is that for the donut profile the melt pool gets wider but not so deep. So, and this is quite interesting if we are thinking about productivity, because we don't want to melt like several layers of powder again and again, but we want to have a wide melt pool so we have less hedges. Then we tried, okay, from single tracks, it's nice finding, but what is if we produce three-dimensional cubic specimens to see if the process works, so that we can get an idea about the productivity. In this case, it was an aluminum silicon scandium alloy. And you can see on the top row for different parameters the relative density we measured, colored here in green, almost 100% density, and red 99% density. You can see that for different parameters on the top for the Gaussian beam profile and the bottom for the donut profile. And very interesting part is here that the H stands for the hedge distance, so the distance between two tracks. If you look at the top right graph, it's red. So for this particular hedge distance of 200 micrometers with the Gaussian beam profile, we were not able to reach a final part density of better than 99%. While for the donut beam profile, very spectacular, we get regimes with almost 100% density, and this is a very big difference between the two beam profiles. So another observation we made is if we're looking at the process, at the byproducts, on the left side you can see the Gaussian profile and the byproducts and the sputter. On the right side from the donut profile, we reduce the number of byproducts per molten volume. With this in mind, we looked, okay, for AlSi10Mg or aluminum alloys that worked, what about a steel alloy? So we used our lab system and looked, okay, about steel and found similar results. So more impressive even, if you see in the middle graph, we could increase the productivity by 240%. And for this particular part in the top right, cost estimation about minus 46%. So this all was done on lab systems, but then the question occurs how to industrialize that. Here we had a very nice project with Aspen Materials, with nLIGHT, and with Optoprim, where we integrated one of nLIGHT's lasers into an industrial available machine and made investigations on aluminum silicon 10. Okay, one more. So this is what I want to show, because this is what my colleague Philip was investigating, and we compared here this final result here with the nLIGHT laser after a whole process development, so a lot of work from our students, and we found out, okay, compared to the data sheets of machine OEMs, we could increase the build rate nearly 3 times. Maybe double the time if you use other numbers, while maintaining or even outperforming the quality in terms of density, which is shown here. So then we looked into another material, into titanium. We wanted to know how the beam profiles influence the melt pool behavior. So in the beginning I showed some cross-section of single weld tracks. We did this for titanium as well. For, if you're familiar with the nLIGHT laser, it's index 4 at the top, 5 in the middle, and 6 at the bottom. And for different combinations of laser power and scan speed. And what you can see very interestingly, if we look at the 7 watt and 600 millimeter per second, is that for the top beam profile, we have a very nice weld trick and a very big weld trick. While for the beam profiles in the middle and the bottom one, we have some protrusion. So this was quite interesting for us, that we have such a big influence between the different beam profiles. Now, of course, for 600 millimeters per second is quite slow in the L-PBF processes. So if we increase the scan speed, still using 700 watts, we noticed that the protrusion effect decreases. But of course, on the other side, also the melt pool decreases. So this is like a perfect optimization problem. Where's the process where we can find the most stable process, the most fast process. And what we are thinking of, how can we find the best hedge distance? So we made some assumptions. So we measured 200 different combinations and cross-section, weld pool width and height, and decided, okay, how to define good weld tracks. So we came up, okay, it should have a certain weld depth. The height of the layer should not be too high, so the recoating lip gets not damaged, and of course we want to have a good width. So then we made an investigation for the hedge distance depending on the melt width and excluding all parameter combinations where were not suitable. So if we're looking at the density for this ratio of melt width by hedge distance, we can see here, which now means like to the left, we have a bigger hedge distance compared to the melt pool. And in the different colors, we see the different indices of the nLIGHT laser. And quite surprisingly, for us at least, at the first glance, was that with the index 4, so the beam profile where we have a comparatively big part of the Gaussian profile in the middle, we actually have better results. So the physics behind this, we are still investigating. So there we'll follow up probably with a research paper. But what does this mean in terms of productivity? So same data, just on the x-axis now the build-up rate, where we can see if we're looking into the range of interest with high relative density, 99.5% and above, we're between 55 and 60 cubic centimeter per hour. If we compare this with data sheets from OEMs, same layer thickness, similar laser power, we notice that we can increase by at least 38% the productivity only by changing the laser system, which is quite nice. I want to mention some challenges. We need to have a better understanding of the physics and also simulation tools, which were also shown and presented here in speeches before, because the complexity increases in the process development. I showed you the sputter slide where I mentioned, okay, sputter reduces, but because we can produce or melt more volume per time, we notice this. So this is a contradiction. But in the end, this is because we can melt more volume per time, and so all through the per volume the sputter reduces per time, because we can be more productive, it increases. So we have to work on the machines. And the last point I want to mention is we notice because we can put more energy into the systems, we are dealing with, or can deal with heating problems. So for certain materials we might need not a base plate heating, but a base plate cooling. So this might be a point of interest in the future. All right, so yeah, thank you for your attention. You find us there, and I'm open for questions.